The light that reaches your eyes at this moment left its source in past. The words forming in your mind exist in what we call the present. And the next breath you take waits somewhere we label the future. If you're watching on a small screen, consider going full screen. And if this journey through the architecture of time resonates with you, subscribing ensures you won't miss what comes next. But those labels, past, present, future, are they mere linguistic conveniences, or do they carve reality at its joints? Does the universe honor our intuition that the present moment is somehow special, that the past is fixed and gone, that the future remains open and unwritten? Or is time something altogether different from what our senses suggest, something woven into the very fabric of existence in a way that makes travel through it not merely fantasy, but perhaps a physical possibility constrained only by the stern mathematics of nature's deepest laws? We live inside time. We cannot step outside it to examine it objectively, the way we might study a river from its bank. Our every thought, every observation, every experiment unfolds as a sequence of moments. This creates an epistemic trap. We must use time to study time, must employ temporal reasoning to question the nature of temporality itself. And yet physics has, over the last century and a half, constructed a picture time so foreign to intuition, so mathematically precise, and so experimentally confirmed that we are forced to reconsider everything we thought we knew about the flow of moments, the fixity of the past, and the openness of the future. The journey begins not with time machines or paradoxes, but with more fundamental question. What is time, physically speaking? Not psychologically, not phenomenologically, but as an element of the natural world subject to physical law. Before the 20th century, time was absolute. It was a cosmic clock ticking uniformly throughout the universe, the same for every observer regardless of their motion or location. Isaac Newton wrote that absolute, true and mathematical time, of itself and by its own nature, flows equably without relation to anything external. This was not merely a convenience of calculation. It was held to be a feature of reality itself. Time was the stage upon which the drama of physics unfolded, immutable and universal, a one-dimensional continuum stretching from infinite past to infinite future, with every observer agreeing perfectly on the duration between any two events, on the simultaneity of distant happenings, on the rate at which the cosmic clock ticked. But absolute time did not survive contact with careful experiment. In the latter half of the 19th century, physicists studying electromagnetism uncovered a puzzle. The equations governing electric and magnetic fields, synthesized by James Clerk Maxwell into a unified framework, predicted that light is an electromagnetic wave traveling at a specific speed, approximately 299,792,458 meters per second in vacuum. But speed relative to what? In Newtonian mechanics, velocities add. If you throw a ball forward from a moving train, an observer on the platform sees the ball moving at the sum of the train's speed and your throw. Surely light should behave the same way. If you shine a flashlight forward while moving toward an observer, that observer should measure light traveling faster than if you were stationary. And yet, Maxwell's equations gave a single fixed speed for light, with no reference frame specified. Physicists initially assumed light propagated through a medium, an invisible substance filling all of space called the luminiferous ether, and that the speed of light was fixed relative to this ether. But experiments designed to detect Earth's motion through the ether, most famously the Michelson-Morley experiment of 1887, found nothing. No matter how the apparatus was oriented, no matter the season or time of day, light always traveled at the same speed. The ether seemed not to exist, or if it did, it conspired in inexplicable ways to hide itself from detection. Albert Einstein, in 1905, cut through confusion with a proposal so radical it seemed almost perverse. The speed of light is the same in all inertial reference frames, regardless of the motion of the source or observer, and this is a fundamental postulate of nature, not an approximation or a consequence of some deeper mechanism. Combined with the principle that the laws of physics are the same in all inertial frames, a principle dating back to Galileo, this leads inexorably to special relativity, a theory that demolishes absolute time and replaces it with something far stranger. If the speed of light is invariant, then observers in relative motion cannot agree on simultaneity. Events that one observer judges to happen at the same time will, for another observer moving relative to the first, occur at different times. There is no universal now slicing through the cosmos. The present moment is not a global feature reality, but a local, observer-dependent notion. More disturbingly, observers in relative motion will disagree on the duration of time intervals and the length of spatial distances. A clock moving relative to you ticks more slowly than an identical clock at rest beside you, an effect called time dilation. A ruler moving relative to you is shorter in the direction of motion than an identical ruler at rest, an effect called length contraction. These are not optical illusions or instrumental artifacts. They are physical facts about the structure of space-time itself. Space-time. That term deserves emphasis, because it encapsulates a conceptual revolution Einstein wrought. Time is not separate from space. The universe is not 3 spatial dimensions plus 1 time dimension existing independently. Rather, space and time are interwoven into a 4-dimensional continuum, space-time, in which the distinction between space and time is relative and observer-dependent. An event is a point in space-time, specified by 4 coordinates. 3 spatial coordinates telling you where, and 1 temporal coordinate telling you when. The history of a particle is a curve in space-time called a world line, threading to the 4-dimensional manifold, connecting the event of its birth to the event of its destruction or present location. In this picture, motion is geometric. When you sit still, you are not motionless in space-time. You are traveling through time, your world line extending along the time axis. When you move through space, your world line tilts, trading some motion through time for motion through space. There's a speed limit, the speed of light, and it arises because there's a maximum tilt your world line can have. A photon's world line is tilted at exactly 45 degrees in standard space-time diagrams, representing motion through space at the speed of light, and such a world line corresponds to 0 elapsed proper time. A photon does not experience time. From its own perspective, if such a notion even makes sense, it is emitted and absorbed in the same instant. For any object with mass, the world line must tilt less than 45 degrees, must remain within a light cone, the boundary defined by light rays emanating from or converging on an event. The light cone divides space-time into regions. The future light cone consists of all events that can be reached from a given event by traveling slower than or at the speed of light into the future. The past light cone consists of all events from which you could have received a signal traveling at or below the speed of light. Outside the light cones lies the elsewhere, events that are space-like separated from you, neither in your causal past nor your causal future. You cannot affect them, and they cannot affect you, at least not at this moment. This causal structure is fundamental. It is what prevents information from propagating faster than light, what enforces the ordering of cause and effect, what gives space-time its arrow, its directionality. And it is intimately connected to the question of time travel, because time travel, if it is possible at all, must respect or somehow circumvent this causal structure without generating contradictions. But special relativity is only the beginning. It applies to flat space-time, space-time without gravity, an idealization that is never perfectly realized in the actual universe. Gravity curves space-time. That is a central insight of general relativity, Einstein's theory of gravitation, completed in 1915. Mass and energy tell space-time how to curve, and space-time curvature tells mass and energy how to move. In this framework, gravity is not a force in the Newtonian sense, but a manifestation of geometry. A planet orbits a star not because the star pulls on it, but because the star's mass curves the spacetime around it, and the planet follows the straightest possible path, a geodesic. Through that curved geometry, the presence of curvature introduces new phenomena. Time dilation is no longer just a consequence of relative motion. It is also a consequence of gravitational potential. Clocks deeper into gravitational, tick more slowly than clocks higher up. This gravitational time dilation has been measured with exquisite precision, first in the Pound-Repke experiment of 1959, which detected the redshift of gamma rays climbing through Earth's gravitational field over a height of merely 22.5 meters, and later with atomic clocks flown on aircraft and satellites. The global positioning system must account for both special relativistic time dilation due to the satellite's orbital velocity and general relativistic time dilation due to their altitude. Without these corrections, the system would accumulate errors of kilometers per day. Gravitational time dilation is not a minor technical detail. It is a window into the nature of time itself. It tells us that time is not an absolute flow, but a local, dynamic quantity, influenced by the distribution of matter and energy. Near a massive object, time slows. Near a black hole, time dilation becomes extreme. At the event horizon of a non-rotating black hole, time, as measured by a distant observer, slows to a halt. An object falling toward the event horizon appears to freeze, its image redshifting and dimming, asymptotically approaching the horizon, but never quite crossing it, at least not in finite time as measured by the distant observer. But from the perspective of the infalling object, proper time along its world line continues to tick forward, and it crosses the horizon in finite proper time, experiencing nothing special at the moment of crossing, only to be destroyed shortly thereafter by tidal forces as it approaches the singularity at the black hole's center. This divergence of perspectives is crucial. Proper time, the time measured by a clock moving along a particular world line, is an invariant. All observers agree on the proper time elapsed along a given world line between two events on that world line. But coordinate time, the time coordinate assigned to events by a particular choice of reference frame, is observer-dependent. In general relativity, there is often no natural or unique way to foliate spacetime into slices of constant time. Different observers will slice spacetime differently, and in highly curved or topologically non-trivial spacetimes, there may be no consistent global notion of time at all. This brings us to the concept of the block universe, a view of reality that follows naturally from relativity. If simultaneity is relative, if different observers slice spacetime into present moments in different ways, then it is difficult to maintain that only the present moment exists, that the past has ceased to be, and the future is not yet. Instead, all events in spacetime, past, present, and future, exist equally. The universe is a four-dimensional block, and our experience of time as flowing, of the present moment as special, is a feature of our consciousness, not a feature of the external world. We are four-dimensional objects, world lines threading through space-time, and our conscious experience is somehow associated with a sequence of three-dimensional slices through our own world line. This eternalist view of time is philosophically contentious, but it is arguably the most straightforward interpretation of relativity. It implies that the future already exists in some sense, laid out in the space-time manifold just as surely as the past. But does this mean the future is fixed, that free will is an illusion, that time travel is already implicitly present in the structure of space-time? Not necessarily. The block universe tells us that all events exist, but it does not by itself tell us the causal structure of space-time, whether there are closed causal loops, whether there are world lines that loop back on themselves in time. To explore that question, we need to examine space-time more carefully, to ask whether the equations of general relativity permit solutions, valid space-time geometries, in which a time-like or null curve, a possible world line for a massive particle or photon, closes on itself, returning to an earlier event. Such a curve is called a closed time-like curve, or CTC, and its existence would represent a form of time travel. A traveler following a CTC would move forward in their own proper time, aging normally, experiencing no violation of local physical law, and yet eventually arrive back at an event in their own past. The first known example of a space-time containing CTCs was discovered by Kurt Gödel in 1949. Gödel, better known for his incompleteness theorems in mathematical logic, found an exact solution to Einstein's field equations describing a rotating universe. In Gödel's universe, space-time is filled with a uniformly distributed, rotating dust of matter, and rotation is rigid, meaning every particle rotates with the same angular velocity. The geometry of this space-time is such that there exist closed time-like curves passing through every event. You could, in principle, travel into your own past simply by moving through space in a sufficiently large loop. The journey might take a long time by your own clock, but you would eventually return to an event that is, according to space-time geometry, earlier than your departure. Gödel's solution is almost certainly not a description of our universe. Our universe is expanding, not rotating in the way Gödel's solution requires, and observations of the cosmic microwave background and the large-scale distribution of galaxies place stringent limits on any net rotation. But the Gödel universe is an existence proof. It demonstrates that general relativity does not, in itself, forbid closed time-like curves. The equations of general relativity are local. They relate the curvature of space-time at a point to the stress-energy tensor, the matter and energy content, at that point. They do not enforce global constraints like the absence of CTCs. That is both liberating and troubling. It means time travel is not ruled out by the fundamental equations, but also means we must look elsewhere, to physical plausibility, to initial conditions, to quantum mechanics, to as yet unknown principles, to determine whether CTCs can actually exist in nature. Other solutions followed. In 1974, Frank Tipler discovered that a massive, infinitely long, rotating cylinder could produce CTCs in its vicinity. The rotation dragged spacetime around the cylinder, a phenomenon known as frame dragging or the lens stirring effect, observed in much weaker form around Earth by satellites like Gravity Probe B. If the cylinder is dense enough and rotates fast enough, the frame dragging becomes so severe that world lines are twisted into closed loops. A spaceship could travel around the cylinder, following a path that, due to drag space-time, curves back in time. Tipler's cylinder, like Gödel's universe, is not realistic. An infinitely long object is a mathematical idealization, and constructing something even remotely resembling a Tipler cylinder will require engineering on a cosmic scale, manipulating vast amount of mass energy in ways far beyond any conceivable technology. But again, it is an existence proof, a demonstration that the mathematics of general relativity accommodates time travel. Then there are wormholes. The term evokes science fiction, but wormholes are rigorous solutions to Einstein's equations. The simplest example is the Schwarzschild wormhole, derived from the Schwarzschild solution, describing a spherically symmetric, non-rotating black hole. If you extend the Schwarzschild geometry analytically to its maximal extent, you find that the spacetime contains not one but two asymptotically flat regions, two separate universes, if you like, connected by a bridge, the Einstein-Rosen bridge, passing to the black hole's interior. This is a wormhole, a tunnel through spacetime connecting distant regions, or even distinct spacetimes. However, the Schwarzschild wormhole is not traversable. The bridge is dynamic, pinching off too quickly for anything, even light, to pass through from one side to the other. An observer entering from one side will be destroyed by the singularity before reaching the other side. The wormhole exists, but it is more of a topological curiosity than a practical time machine. To make a traversable wormhole, you need to hold the throat open, to prevent it from collapsing. This requires matter or energy with unusual properties, specifically a negative energy density, a violation of the so-called null energy condition, which states that for any null vector representing a light-like direction, the stress-energy tensor contracted with that vector is non-negative. Negative energy sounds exotic, perhaps impossible, but quantum field theory allows it in certain circumstances. The Casimir effect, predicted in 1948 and observed experimentally, involves two uncharged, parallel conducting plates in vacuum. Quantum fluctuations of the electromagnetic field are suppressed between the plates compared to the surrounding space, leading to a net attractive force. The energy density between the plates is negative relative to the vacuum elsewhere. This is not a violation of energy conservation. The total energy can still be non-negative, but it demonstrates that local negative energy densities are permitted by quantum mechanics. If you could engineer a configuration of matter or fields with a sufficiently negative energy density, you might be able to stabilize a wormhole throat, rendering it traversable. This is highly speculative. The amount of negative energy required is enormous. The stability of such a configuration is questionable, and no one knows how to actually construct such a thing. But it is not ruled out by known physics, and it opens the door to time travel in a particularly straightforward way. Imagine two wormhole mouths, initially at rest relative to each other and synchronized in time. They are connected by a short tunnel through space-time. If you enter one mouth, you emerge almost instantly from the other, as if stepping through a doorway across space. Now suppose you take one mouth and accelerate it to a high speed, near the speed of light, and then bring it back. Special relativity tells us that the moving mouth will experience less elapsed proper time than the stationary mouth. If you synchronize clocks at each mouth before the journey, the clock at the moving mouth will be behind the clock at the stationary mouth when they are reunited, but the wormhole connects them. The wormhole itself does not experience time dilation in a simple way. The connection is through space-time, and the geometry is such that the two mouths remain connected despite their different aging. The result is a time machine. If you enter the stationary mouth, you travel through the wormhole and emerge from the moving mouth, but you emerge at a time earlier than the time coordinate of the stationary mouth's exterior. You have traveled into the past. You could then, in principle, travel through ordinary space back to the location of the stationary mouth and meet your younger self, arriving before you left. The wormhole has become a bridge not just across space, but across time. This scenario, first analyzed in detail by Kip Thorne and his collaborators in the late 1980s, highlights a deep connection between faster-than-light travel and time travel. In relativity, the two are essentially equivalent. If you can travel faster than light, you can travel backward in time, and vice versa. The reason is the relativity of simultaneity. Events that are space-like separated, outside each other's light cones, have no invariant time ordering. One observer may judge event A to be earlier than event B, while another observer in relative motion judges B to be earlier than A. If you can travel instantaneously in your own reference frame from A to B, then from the perspective of another observer, you have traveled backward in time. This is not a quirk of coordinates. It is a deep feature of space-time structure. Any mechanism that allows faster-than-light travel, wormholes, warp drives, any hypothetical shortcut through space-time can, with suitable manipulation, be converted into a time machine. This brings us face-to-face with the paradoxes. If time travel is possible, if you can journey into your own past, what prevents you from altering that past in ways that would prevent your own existence or render your journey impossible? The grandfather paradox is a classic formulation. You travel back in time and kill your grandfather before your parent is conceived, thereby preventing your own birth. But if you were never born, you could not have traveled back to kill your grandfather. The paradox seems to render time travel logically impossible, a contradiction in terms. And some physicists take this as evidence that nature must prohibit CTCs, that there is some as yet undiscovered principle, a chronology protection conjecture, that prevents time machines from forming. Stephen Hawking proposed a chronology protection conjecture in 1992. He argued that whenever you try to create CTCs, quantum effects intervene to prevent their formation. For instance, if you try to construct a time machine using a wormhole, as the wormhole approaches a point of enabling time travel, vacuum fluctuations, quantum fluctuations of fields propagating through the wormhole will be amplified, looping repeatedly through the wormhole, building up an infinite energy density that would destroy the wormhole or at least render it non-traversable. This is analogous to the howl of feedback in a sound system when a microphone is placed too close to a speaker. The energy builds catastrophically, preventing the system from functioning. The chronology protection conjecture remains unproven. It is difficult to analyze because it requires a full theory of quantum gravity, a theory that consistently merges quantum mechanics and general relativity. And we do not yet have such a theory. String theory, loop quantum gravity, and other approaches offer insights but no definitive answers. In the absence of a complete theory, we can only make heuristic arguments, and those arguments suggest that Hawking might be right, that quantum mechanics enforces chronology protection, but they do not prove it. There are even scenarios like the Deutsch-Politzer model or the framework of post-electric quantum mechanics, where CTCs might be consistent if quantum mechanics is interpreted appropriately, though these scenarios involve subtleties and interpretational choices that are far from settled. Another response to the paradoxes is the Novikov self-consistency principle proposed by Igor Novikov in the 1980s. Novikov argued that in a space-time with CTCs, only self-consistent histories are possible. The universe will not permit you to kill your grandfather because any attempt to do so will fail. You will slip on a banana peel, the gun will jam, something will intervene to ensure that the past remains exactly as it was, because it must be consistent with a future that includes your departure on the time travel journey. The self-consistency principle is not a dynamical law. It is a boundary condition on space-time. It says that the initial conditions and the laws of physics together conspire to ensure consistency. There are no free parameters. You cannot choose your actions arbitrarily in the past. Your actions are already part of the fixed four-dimensional space-time structure. This view aligns with the block universe interpretation. If all events exist eternally, if the past is as fixed as the future, then there is no contradiction. You travel back and do whatever you were always going to do. Your presence in the past is already part history. It has always been there. You cannot change the past because the concept of change implies a metatime, a time in which the past itself evolves, and no such metatime exists. The past is simply what it is, a region of the space-time manifold, and your world line threads through it in a self-consistent loop. Experimental tests of these ideas are, naturally, beyond current technology. We cannot build a wormhole, cannot construct a Tipler cylinder, cannot access a Gödel universe. But we can observe phenomena that involve extreme curvature and test the limits of general relativity. Black holes, neutron stars, gravitational waves. These are the laboratories where space-time reveals its more exotic properties. The detection of gravitational waves by LIGO in 2015 and subsequent observations have confirmed aspects of general relativity in the strong field regime with remarkable precision. So far, everything is consistent with Einstein's equations, with no hint of chronology violations. Cosmic strings are another speculative possibility. These are hypothetical one-dimensional topological defects in space-time, remnants of phase transitions in the early universe, predicted by some models in particle physics and cosmology. A cosmic string would have immense tension, contributing a large negative pressure to its stress-energy tensor, and would curve space-time around it in a distinctive way. Two cosmic strings moving past each other at relativistic speeds could, under certain conditions, produce CTCs in the region between them. The geometry is such that a traveler could loop around the strings and return to their own past. Cosmic strings have not been observed, and if they exist, they are likely exceedingly rare and unlikely to be moving in just the right way to form CTCs. But again, they illustrate that general relativity does not inherently forbid time travel. Quantum mechanics adds additional layers of complexity. In the double-slit experiment, a photon or electron passes through two slits and interferes with itself, producing a pattern on a screen that cannot be explained if the particle traveled through only one slit. The particle is described by a wave function, a mathematical object that encodes probabilities, and the wave function passes through both slits, interfering with itself. Measurement collapses the wave function, yielding a definite outcome, a single location on the screen, but before measurement, the particle is in a superposition, existing in some sense in multiple states simultaneously. How does this relate to time travel? If CTCs exist, particles can interact with their past selves. A photon could travel through a wormhole and meet itself earlier in its own history. This leads to strange causal loops. The photon's past is influenced by its future, and its future is influenced by its past, forming a closed loop. How does quantum mechanics handle this? David Deutsch, in 1991, proposed a model in which quantum mechanics and CTCs could coexist. He used a framework of density matrices and showed that there exist self-consistent quantum states for systems with CTCs, states that do not lead to contradictions. In Deutsch's model, a particle traveling back in time enters a different branch of the wave function, not necessarily the same branch it left. This is related to the many worlds interpretation of quantum mechanics, where every quantum measurement causes a universe to split into multiple branches, each corresponding to a different outcome. In a space-time with CTCs, the branches form closed loops, and consistency is maintained by ensuring that the quantum state of the particle is the same each time it traverses a loop, average appropriately over all branches. This is highly abstract and difficult to visualize. The mathematics works, in the sense that there are solutions, but the physical interpretation is murky. Does it mean that time travel is possible in quantum mechanics? Or does it simply mean that we can write down consistent equations without knowing whether they correspond to anything real? The jury is still out. Some researchers take Deutsch's work as evidence that CTCs might not be as problematic as the classical paradoxes suggest. Others argue that the many worlds interpretation is itself controversial, that the notion of branches and splitting is an interpretational gloss on the mathematics rather than a physical fact, and that Deutsch's model does not resolve the deeper issues. There is also the question of what happens to information in the presence of CTCs. In quantum mechanics, information is conserved. Unitary evolution, the standard time evolution of quantum systems, preserves information. You can, in principle, reverse the evolution and recover the initial state. But CTCs might allow information to be copied or destroyed. Imagine a bit of information traveling through a time loop. It enters the loop, travels back in time, and meets itself. You could, in principle, read the bit, copy it, and send both copies forward in time. This would violate the no-cloning theorem, a fundamental result in quantum information theory, stating that you cannot create an identical copy of an arbitrary unknown quantum state. Conversely, you could use a CTC to erase information, sending it back in time to interfere destructively with itself. This would violate unitarity. These informational paradoxes suggest that either CTCs do not exist, or quantum mechanics must be modified in space-times with CTCs, or the seeming violations are resolved by some subtle consistency condition we do not yet understand. It is an active area of research with connections to quantum computing, quantum cryptography, and the foundations of quantum theory. Some researchers have even proposed that if CTCs do exist, they might enable computational feats beyond the reach of ordinary quantum computers, solving problems in polynomial time that would otherwise require exponential time. This is speculative, bordering on wild conjecture, but it illustrates the profound implications CTCs would have for our understanding of physics and information. Returning to the classical realm, we should consider whether time travel to the future, as opposed to the past, is problematic. It is not. In fact, we time travel to the future constantly, simply by existing. Every second that passes takes us 1 second into the future. But we can also travel to the future faster, relative to others, by exploiting time dilation. If you board a spaceship and accelerate to a speed close to the speed of light, travel for a while, and then return to Earth, you will have aged less than people who remain on Earth. You will have traveled into their future. This is not speculative. It is a direct prediction of special relativity, confirmed by countless experiments. Muons created in the upper atmosphere by cosmic rays reach the ground even though their half-life is so short they should decay long before arriving. The reason is time dilation. They are moving at relativistic speeds, and in their rest frame, they do not travel far. But in Earth's frame, they live longer due to time dilation. Conversely, in the muon's frame, the atmosphere is length contracted, so the distance to the ground is shorter. Either way, the muons reach the ground, a direct confirmation of relativistic effects. Astronauts on the International Space Station age slightly more slowly than people on Earth's surface, by a tiny amount, a few milliseconds over months in orbit, due to their high speed and slightly weaker gravitational field. If we could build a spacecraft capable of accelerating to, say, 99% of the speed of light, traveling for a year of ship time and then returning, hundreds of years would pass on Earth. The travelers would emerge into Earth's far future, stepping out of the spacecraft into a world transformed by centuries of history they did not experience. This is one-way time travel, irreversible, unidirectional, not the dramatic looping back to confront your younger self, but it is time travel nonetheless, permitted and indeed inevitable given the structure of space-time. Gravitational time dilation offers another route. If you could survive near the event horizon of a black hole, time would pass extremely slowly for you relative to distant observers. If you stayed there for a while by your clock and then escaped, assuming you could escape, which is not possible from inside the horizon, but is possible if you remain just outside, you would find that far more time has passed in the outside universe. You would have traveled to the future. The film Interstellar dramatized this, depicting astronauts visiting a planet orbiting close to a supermassive black hole, where 1 hour on the planet corresponds to 7 years in the distant universe. The magnitude is fictional, chosen for narrative effect, but the principle is sound. Gravitational time dilation is real, and in principle, you could use it to journey far into the future. But traveling to the past is different. It requires closed time-like curves or something equivalent, and it brings the paradoxes. The paradoxes are not merely logical puzzles. They have physical content. They force us to ask whether the universe is deterministic, whether the past is truly fixed, whether causality is inviolable. In classical general relativity, without quantum mechanics, space-time is a four-dimensional manifold with a metric. The metric determines geodesics, and matter and light follow those geodesics. If the manifold contains CTCs, then world lines can loop. There is nothing locally unusual about a CTC. At every point along the curve, the laws of physics are satisfied. Curvature is related to stress energy by the Einstein field equations, and everything is smooth and continuous. The strangeness only emerges globally when you realize that the world line closes, that the traveler meets their past self. The self-consistency principle says that whatever happens on a CTC must be self-consistent. If you travel back and try to prevent your departure, you will fail. The universe is a self-consistent four-dimensional structure, and your actions in the past are already part of that structure. This resolved the paradox logically, but it raises a question of agency. Do you have free will? Can you choose your actions, or are they predetermined by the requirement of consistency? In a block universe with CTCs, your world line is laid out, and every event on that world line, including your choices, is fixed. You experience the illusion of choice, but the outcome is already determined by the space-time geometry. This is a form of determinism, albeit a strange one, where the future constrains the past just as much as the past constrains the future. Some philosophers and physicists argue that this does not eliminate free will in any meaningful sense. After all, even in a deterministic universe without time travel, if Laplace's demon could know the position and momentum of every particle, the future would be entirely determined by the past. The block universe with CTCs is just a more symmetric version of determinism, where temporal order is less privileged. Others find this unsatisfying, arguing that the ability to form intentions and act on them is compromised if the universe must conspire to ensure consistency. This is more a philosophical debate than a physics one, but it underscores the discomfort many feel with the implications of time travel. There is also the question of whether the self-consistency principle is too restrictive. If only one self-consistent history is possible, or if a set of self-consistent histories is highly constrained, does this require fine-tuning? Do the initial conditions of the universe have to be incredibly special to allow CTCs while maintaining consistency? Some analyses suggest yes, that the phase space of consistent histories is measure zero, meaning you would need to fine-tune parameters to infinite precision. If that is the case, CTCs might be mathematically possible but practically impossible, requiring a level of coordination between disparate parts of space-time that would never arise naturally. This is not a proof that CTCs do not exist, but it is a reason to be skeptical. Quantum mechanics complicates the picture further. The uncertainty principle tells us that we cannot know both position and momentum of a particle with arbitrary precision. The wave function encodes probabilities, not certainties. How does this mesh with the requirement of self-consistency? Deutsch's model, as mentioned, uses density matrices to describe mixed states and finds consistent solutions. But Seth Lloyd and others have explored alternative models, post-selected quantum mechanics with CTCs, where the quantum state is constrained by both initial and final conditions, and the result is a kind of quantum self-consistency enforced by the requirement that the state match itself after traversing the loop. These models predict odd phenomena, like violations of the no-cloning theorem or the ability to distinguish non-orthogonal quantum states, tasks normally impossible. Experimentally testing these ideas is extraordinarily difficult. We cannot create actual CTCs, but we can simulate them using quantum systems. Researchers have used quantum optics setups to mimic the structure of CTC, sending photons through a sequence of operations designed to emulate traveling back in time and interacting with themselves. The results are consistent with the Deutsch model in some cases, and with post-selected models in others, depending on the setup. These experiments do not prove anything about real CTCs, but they probe the logical structure of quantum mechanics in unusual causal situations and test whether the theoretical models are internally consistent. Beyond wormholes and cosmic strings, other speculative mechanisms for time travel have been proposed. The Alcubierre warp drive, conceived by Miguel Alcubierre in 1994, is a solution to Einstein's equations in which a bubble of space-time contracts space in front of a spacecraft and expands behind, allowing the spacecraft to travel faster than light relative to distant observers, without locally exceeding the speed of light. The spacecraft surfs on a wave of space-time. Like wormholes, the Alcubierre drive requires exotic matter, specifically a negative energy density, to sustain the warp bubble. And like any faster-than-light mechanism, it can be converted into a time machine. If you create two warp bubbles moving in opposite directions at superluminal speeds, they can be used to create CTCs. Again, this is highly speculative, requires exotic matter, and faces problems with stability and causality, but it is a solution to the equations. There are also scenarios involving the early universe. If the universe underwent inflation, a period of exponential expansion in the first fractions of a second after the Big Bang, driven by a scalar field called the inflaton, then the energy density and space-time curvature during inflation were enormous. Some speculative models suggest that quantum fluctuations during inflation could have produced closed time-like curves or even disconnected regions of space-time, baby universes budding off from our own, some of which might reconnect later, forming bridges through time. This is extremely speculative, verging on science fiction, but it illustrates that the extreme conditions of the early universe might permit phenomena that are impossible in the more sedate conditions of the present epoch. Another angle is the role of topology. Space-time topology refers to the global structure of space-time, whether it is simply connected, whether it has handles or wormholes, whether it is orientable. General relativity, as a local theory, does not specify topology. It only constrains local curvature. You can have many different space-time topologies consistent with the same local field equations. Some topologies admit CTCs. For instance, if space-time is multiply connected, with wormhole-like structures, you can have world lines that loop through the wormholes and close on themselves. The question is whether such topologies can arise dynamically, whether they can be formed by physical processes, or whether they require special initial conditions that are not realized in our universe. There is also the arrow of time, the observed asymmetry between past and future. Entropy increases over time, the second law of thermodynamics, a statistical statement about the behavior of large ensembles of particles. Eggs break. They do not spontaneously reassemble. Gases diffuse. They do not spontaneously compress. Heat flows from hot to cold, not the reverse. These are all manifestations of increasing entropy, and they define a direction in time, an arrow pointing from lower entropy past to higher entropy future. But the fundamental laws of physics, Newton's laws, Maxwell's equations, the Schrödinger equation, even the Einstein field equations, are time-symmetric or nearly so. They work equally well forward or backward in time. The arrow of time is not in the laws themselves, but in the boundary conditions, specifically the fact that the universe began in a state of very low entropy, the Big Bang. How does this relate to time travel? If you travel backward in time, do you reverse the arrow of time? Do you see entropy decreasing? Not necessarily. Entropy is a statistical property of macroscopic systems. As a microscopic traveler, a single particle, or even a human, you carry entropy with you. If you travel back in time via CTC, you locally reverse your own temporal direction, but the universe around you continues to evolve toward higher entropy. You would see a universe at an earlier stage of its entropy increase, but you would not see time running backward in the sense of watching events unfold in reverse. You would experience time normally, always moving forward along your world line, even as that world line loops back to an earlier coordinate time. This distinction is important. Time travel via CTC is not like playing a video in reverse. It is like taking a path through space-time that happens to loop back. Your personal time, proper time, always increases. You age. You remember the past and not the future. You experience causality in the normal forward direction. It is only the coordinate time, the label assigned to events by a particular reference frame, that can decrease along your world line. This is counterintuitive, but essential to understanding how time travel would actually work in the context of relativity. Thermodynamics also raises questions about the stability of CTCs. If you have a CTC, you could send a cold object back in time, let it warm up, and send it back again, creating a perpetual motion machine of the second kind, violating the second law. Or you could accumulate entropy indefinitely by looping through the CTC, leading to infinite entropy density. These thermodynamic paradoxes are analogous to the grandfather paradox, but phrased in terms of entropy rather than causality. The resolution might be similar, self-consistency. The entropy flowing through the CTC must be self-consistent, meaning the entropy entering the loop must equal the entropy exiting, averaged appropriately. This places constraints on the state of matter and fields near the CTC, constraints that might be difficult or impossible to satisfy, providing another potential barrier to the formation of time machines. Black holes play a special role in discussions of time travel, not just because of gravitational time dilation, but because of their interiors. The Schwarzschild solution, as mentioned, describes a non-rotating black hole. Inside the event horizon, the roles of time and space are interchanged in a sense. The radial coordinate becomes time-like, and the time coordinate becomes space-like. You cannot avoid moving toward the singularity any more than you can avoid moving forward in time outside the horizon. The singularity is not a place in space. It is a moment in your future, an inevitable event in your world line once you cross the horizon. This is deeply strange and suggests that the interior of a black hole is a region where time behaves in radically different ways than we are accustomed to. Rotating black holes, described by the Kerr solution found by Roy Kerr in 1963, are even stranger. A rotating black hole has an event horizon and an inner horizon, and between them is the ergosphere, a region where space-time is dragged around the black hole so strongly that you cannot remain stationary. You must rotate with the black hole. The interior contains a ring singularity rather than a point singularity, and the Kerr geometry, extended maximally, contains regions connected by wormholes and, in some interpretations, regions with CTCs. If you could pass through the ring singularity without being destroyed, which is almost certainly impossible, but bear with a thought experiment, you might enter a region of space-time with very unusual causal structure, possibly even regions where time travel is permitted. The Kerr metric also exhibits a phenomenon called the Cauchy horizon, an inner boundary beyond which predictability breaks down. The Einstein field equations are deterministic. Given initial data on a space-like surface, you can evolve the equations forward and backward to determine the state everywhere in the space-time, at least within the domain of dependence of that initial surface. But if the space-time contains a Cauchy horizon, there are regions beyond it that are not determined by the initial data. Anything could emerge from beyond the Cauchy horizon. This is related to the presence of CTCs or other causal anomalies. It suggests that the interior of rotating black holes might be fundamentally unpredictable. Even in classical general relativity, a breakdown of determinism that some physicists find unacceptable and interpret as evidence that the maximally extended Kerr geometry is not physically realized, that quantum effects or other mechanisms prevent the formation of Cauchy horizons. Penrose diagrams are a useful tool for visualizing the global causal structure of spacetimes. In a Penrose diagram, the entire infinite spacetime is conformally mapped onto a finite region, with no rays, light rays, traveling at 45-degree angles. You can see the causal structure at a glance. Light cones, horizons, singularities, regions of spacetime that can influence or be influenced by each other. For a black hole, the Penrose diagram shows the event horizon as a diagonal line, the singularity as a horizontal line at the top, and the interior as the region between them. For a wormhole or a space-time with CTCs, the Penrose diagram becomes more complicated, with multiple regions connected in non-trivial ways. These diagrams are invaluable for understanding which regions of space-time are in causal contact, which world lines are possible, and where paradoxes might arise. String theory, the leading candidate for a theory of quantum gravity, offers some insights but also new puzzles. String theory posits that the fundamental constituent of the universe are not point particles, but one-dimensional extended objects, strings, vibrating at different frequencies. The theory requires extra spatial dimensions beyond the familiar 3, typically 6 or 7 additional dimensions compactified at scales far too small to observe directly. String theory has many solutions, a vast landscape of possible vacua, each corresponding to a different universe with different physical constants and properties. Some of these solutions might permit CTCs, while others might not. The theory also includes objects called D-branes, higher dimensional surfaces on which strings can end, and more exotic structures like black branes and Orionifolds. One intriguing result from string theory is the AD-SCFT correspondence, a duality between a gravitational theory and an anti-de Sitter space, a space-time with a negative cosmological constant, and conformal field theory without gravity living on the boundary of that space. This duality has been used to study quantum aspects of black holes, including the information paradox. The question of whether information is lost when matter falls into a black hole, and the black hole eventually evaporates via Hawking radiation. The resolution seems to be that information is not lost, that it is encoded in correlations in the Hawking radiation, a result that has implications for the unitarity of quantum mechanics and possibly for the consistency of time travel. If quantum mechanics is unitary, if information is preserved, then CTCs might be constrained in ways that prevent paradoxes, or they might be excluded altogether. Loop quantum gravity, an alternative approach to quantum gravity, emphasizes a discrete, quantized nature of space-time at the Planck scale, about 10 to the minus 35 meters and 10 to the minus 43 seconds. In loop quantum gravity, space-time itself is woven from discrete loops of gravitational field, spin networks, and the smooth continuum we observe is an emergent, coarse-grained description. Time is also quantized, emerging from the fundamental structure rather than being a fixed background. This raises fascinating questions about time travel. If time is discrete, can you travel backward by integer steps? Are CTCs even definable, or does a discrete structure forbid them? These questions are the frontier of research, and answers are tentative at best. Quantum cosmology attempts to apply quantum mechanics to the universe as a whole, describing the universe's wave function evolving according to the Wheeler-DeWitt equation, a quantum version of the Einstein field equations. In this framework, time is even more puzzling. The Wheeler-DeWitt equation does not contain an explicit time parameter. It is timeless, a constraint equation rather than an evolution equation. Time emerges as a relational concept, defined by the correlations between different parts of a universal wave function. How does this relate to time travel? If time is emergent, if the fundamental description is timeless, then traveling backward in time might be a meaningless concept, or it might correspond to exploring different branches of the wave function, different histories that are all present in the superposition. This is highly speculative and depends on interpretational choices about quantum mechanics and the nature of time. The cosmological constant, or dark energy, also enters the picture. Our universe appears to have a small positive cosmological constant, causing the expansion of the universe to accelerate. The cosmological constant contributes a stress energy that is uniform in space and constant in time, a sort of energy density intrinsic to the vacuum. In space-times of the positive cosmological constant, such as de Sitter space, the causal structure is different from flat space-time. There are cosmological horizons, boundaries beyond which events cannot influence you. The global geometry is more constrained, and it is less clear whether solutions with CTCs exist or can be constructed. Conversely, in anti-de Sitter space, with negative cosmological constant, the boundary plays a crucial role, and the additive T correspondence becomes relevant. The sign and magnitude of the cosmological constant affect the space of possible space-time geometries, and thus the feasibility of time machines. We should also consider the role of initial conditions. The universe began with the Big Bang, an initial singularity of infinite density and temperature, at least in the classical description. The initial conditions were very special, corresponding to a state of extremely low entropy, which is why entropy has increased ever since. If CTCs exist, they might require equally special initial conditions, a fine-tuning that would be improbable in any generic universe. This is not a proof against CTCs, but it suggests they might be rare or absent in a randomly chosen universe, only appearing in specially prepared situations, possibly artificially created by advanced civilizations. Advanced civilizations bring us to the realm of speculation about whether anyone or anything could actually build a time machine, even in principle. Suppose a civilization could harness the energy output of stars, could manipulate matter at the atomic or subatomic level with perfect precision, could create and stabilize exotic matter with negative energy density, could engineer the fabric of space-time itself. Even then, building a time machine would be extraordinarily difficult. You would need to collect or create vast amounts of negative energy, shape it into the right configuration to stabilize a wormhole or create a warp bubble, accelerate one mouth of the wormhole to relativistic speeds, or manipulate it in other ways to create a time difference, all while maintaining stability and avoiding runaway quantum fluctuations that might destroy the apparatus. The engineering challenges are staggering, likely beyond anything achievable even for a Kardashev Type 3 civilization, one that commands the energy resources of an entire galaxy. Moreover, Even if you could build such a device, you could not use it to travel to times before the time machine was created. A wormhole time machine, for instance, only connects a mouse to times after their respective creation and manipulation. You cannot travel back to kill your grandfather if your grandfather lived before the time machine existed. This limits the scope of time travel considerably. You could visit the future or return the moment the time machine was turned on, but not travel arbitrarily far into the past. This alleviates some paradoxes, but does not eliminate them. You could still create causal loops, still meet your older self who traveled back from your future. The Fermi paradox. The question of why we do not observe evidence of advanced extraterrestrial civilizations despite the high probability of their existence has been connected to time travel. If time travel is possible and advanced civilizations can build time machines, why don't we see time travelers from the future? One answer is that time travel is simply impossible, ruled out by physics. Another is that it is possible, but no civilization has achieved the capability. Another is that time travelers are here but remain hidden, either for ethical reasons, non-interference, prime directive-style guidelines, or because their presence is subtle, indistinguishable from ordinary phenomena. Or perhaps civilizations capable of building time machines destroy themselves before actually constructing one, a dark filter suggesting that such technology is inherently dangerous. These are speculative sociological and anthropic arguments, not physics, but they frame the question of time travel in a broader context. Let us return to the physics and consider energy conditions more carefully. Energy conditions are inequalities that the stress-energy tensor is expected to satisfy, ruling out certain exotic matter. The null energy condition, as mentioned, requires that energy density measured by any light-like observer is non-negative. The weak energy condition extends this to time-like observers. The strong energy condition is even more restrictive, and the dominant energy condition requires that energy does not flow faster than light. Violations of these conditions are necessary for traversable wormholes and warp drives. Quantum field theory permits violations of the null and weak energy conditions in localized regions and for limited durations. But large-scale, sustained violations sufficient to hold open a wormhole are far from established. There are quantum inequalities, constraints derived from quantum field theory, that limit how much negative energy can accumulate and for how long, suggesting that even in quantum mechanics, you cannot have arbitrarily large regions of negative energy without compensating positive energy nearby. The Casimir effect, again, is the prime example of negative energy. Two parallel plates in vacuum experience an attractive force due to suppression of vacuum fluctuations between them. The energy density between the plates is negative relative to the surrounding vacuum, but the total energy is not negative. Integrating over all space, including the positive energy density outside the plates, yields a non-negative result. The negative energy is borrowed from the surrounding vacuum and must be repaid. Quantum inequalities formalize this idea, stating that the magnitude and duration of negative energy are inversely related. If you want a large negative energy, you can only maintain it for a short time, and vice versa. This places stringent limits on the size and stability of any device relying on negative energy. Some researchers have proposed using the dynamical Casimir effect, where moving mirrors or time-varying boundary conditions create photon pairs from the vacuum, potentially yielding negative energy densities that could be harnessed. Others have explored squeezed quantum states of light or other fields, which exhibit negative energy fluctuations in certain directions. These ideas are at the cutting edge of quantum field theory and experimental physics, and while they demonstrate that negative energy is not forbidden, they do not provide a clear path to building a macroscopic time machine. The gap between a localized microscopic quantum effect and a stable, traversable wormhole is immense. There is also the question of radiation. Hawking radiation, predicted by Stephen Hawking in 1974, arises from quantum field theory in curved spacetime. Virtual particle pairs are constantly created and annihilated in the vacuum. Near the event horizon of a black hole, one particle of the pair can fall into the black hole while the other escapes, resulting in a net emission of radiation. The black hole loses mass over time, eventually evaporating completely. The temperature of this radiation is inversely proportional to the black hole's mass. Stellar mass black holes radiate at a negligible temperature, far colder than the cosmic microwave background, but tiny primordial black holes would radiate much more intensely. If a wormhole or time machine involves horizons or other features that mimic black hole horizons, it might emit similar radiation, potentially destabilizing the device or heating it to the point of destruction. The chronology protection conjecture, again, is Hawking's proposal that such quantum effects will always intervene to prevent CTCs from forming. As the wormhole approaches the point where CTCs would appear, vacuum fluctuations traveling through the wormhole are amplified, looping back on themselves, building up exponentially until the energy density diverges, destroying the wormhole. This is a back reaction effect, where the presence of the time machine alters the quantum fields in such a way that the time machine cannot form. Calculating this precisely requires a full theory of quantum gravity, and current attempts using semi-classical approximations, treating gravity classically and matter quantum mechanically, suggest that chronology protection might hold, but the calculations are plagued with infinities and ambiguities. The conjecture remains unproven. If chronology protection does hold, it would mean that nature has a deep aversion to time travel, that the universe is structured in such a way that CTCs are excluded not by fiat, but by dynamical law. This would be a profound result, revealing a hidden principle in physics, a connection between causality and quantum mechanics that is not obvious from the foundations of either theory. It would suggest that time has a preferred direction encoded in the quantum structure of fields, that the arrow of time is not merely a statistical artifact of boundary conditions, but a fundamental feature of the laws themselves. Conversely, if chronology protection does not hold, if CTCs can form and remain stable, we are forced to accept the paradoxes and the strange causal loops, the self-consistent histories, the erasure of free will in the strong deterministic sense. Or we must accept Deutsch's quantum mechanical resolution, where time travel involves transitions between branches of the wave function, and consistency is maintained in a weaker, probabilistic sense. Or some other resolution we have not yet imagined. The question is open. Observationally, we have no evidence for CTCs. We have never detected a time traveler, never observed an event that could only be explained by backward causation, never seen a wormhole or cosmic string. The universe appears to respect causality at all scales we can observe. But absence of evidence is not evidence of absence, especially when phenomena in question would be extraordinarily rare or requires scales of energy and manipulation far beyond our current capabilities. It is possible that CTCs exist in some exotic corner of the universe, or in the deep interiors of black holes where we cannot observe, or they existed briefly in the early universe and have long since decayed or become inaccessible. The anthropic principle, the idea that the universe must be compatible with the existence of observers like us, might also play a role. If time travel were common, if CTCs were easy to form, the universe might be filled with causal paradoxes, a tangled mess of self-referential loops that might prevent the formation of stable structures like stars, planets, and life. The fact that we exist and observe a causally well-behaved universe might be evidence that CTCs are rare or absent. This is a weak argument, more philosophical than physical, but it suggests that the conditions required for observers like us might be incompatible with widespread time travel. We should also consider the notion of a time machine as distinct from a region of space-time with CTCs. A time machine, in the practical sense, is a device that allows controlled travel to the past, that you can turn on and off, enter and exit at will. A region of space-time with naturally occurring CTCs might exist without being a time machine in this sense. You might need to be at the right place at the right time, traveling in the right direction, to make use of the CTC. It might not be something you can enter from arbitrary initial conditions. This distinction is important for thinking about the engineering and the paradoxes. A naturally occurring CTC is a feature of space-time geometry, part of the initial conditions or the global structure. A time machine is a localized device, a manipulation of space-time that creates CTCs where none existed before. The latter seems far more difficult and might be subject to stronger constraints. The mathematics of causality in general relativity is rich and subtle. A space-time is said to be globally hyperbolic if it possesses a Cauchy surface, a space-like surface such that every inextendable causal curve intersects it exactly once. This means the space-time has a well-defined notion of time, that you can foliate it into a sequence of space-like slices, and that the evolution is deterministic. If a space-time is not globally hyperbolic, if it contains CTCs or other causal anomalies, then there is no Cauchy surface, and determinism breaks down in some sense. Many physically reasonable spacetimes in general relativity are globally hyperbolic. It is often taken as a regularity condition, an assumption that the spacetime is well-behaved. But it is not required by the Einstein field equations, and solutions without global hyperbolicity exist and are valid as solutions. The question is whether such solutions can arise from physically reasonable initial conditions, whether they can be constructed by evolving smooth, regular initial data forward in time, or whether they require special, finely tuned conditions that would never occur naturally. This is the question of chronology protection phrased more precisely. Does the Einstein field equations, possibly combined with quantum effects and energy conditions, dynamically prevent the formation of CTCs from generic initial data? There are theorems, like the singularity theorems of Penrose and Hawking, that show under certain conditions singularities must form, regions where curvature becomes infinite and the classical description breaks down. These theorems assume energy conditions and causal structure. There are also partial results suggesting that the formation of CTCs from smooth initial data is difficult, that you need closed trap surfaces or other special features. But there is no general theorem prohibiting CTCs, no proof that they cannot form. The question remains open, a major unsolved problem in classical and quantum gravity. The role of symmetry is also worth considering. Many of the known solutions with CTCs, like Gödel's universe or the Kerr black hole interior, have high symmetry, rotation, homogeneity, isotropy in some cases. Real astrophysical objects in cosmological scenarios are less symmetric, more irregular. It might be that CTCs require a level of symmetry that is not realized in nature, that any perturbation or asymmetry disrupts the delicate balance needed for the CTC to exist. This is speculative, but it suggests that even if CTCs are mathematically possible, they might be structurally unstable, unable to persist in a realistic, messy universe. Chaos and instability are relevant here. General relativity is a nonlinear theory, the gravitational field affects itself, and small changes in initial conditions can lead to large changes in outcomes. In some spacetimes, world lines can be chaotic, extremely sensitive to initial conditions. If you are trying to navigate a CTC, to close the loop precisely, any tiny error might send you off course, preventing the loop from closing. This is different from the thermodynamic or quantum instabilities. It is a classical dynamical instability, a sensitivity inherent in the nonlinear dynamics of curved spacetime. It suggests that even if CTCs exist, using them for controlled time travel might be practically impossible. Another consideration is a multiverse, the idea that our universe is one of many, possibly infinitely many, universes with different physical constants, different histories, different laws even. In the context of eternal inflation, quantum fluctuations during inflation create bubbles that inflate separately, each becoming a distinct universe. Some of these universes might have topologies or field configurations that admit CTCs, while others do not. If we live in a universe where CTCs are absent or inaccessible, that might simply be a selection effect, an anthropic explanation. Universes with ubiquitous CTCs might not support observers, while universes without CTCs allow stable structures and life. This is highly speculative and untestable, but it places time travel in a broader cosmological context. The philosophical implications of time travel extend beyond physics into metaphysics, epistemology, and ethics. If you can travel to the past, does the past still exist? The Bloch universe says yes, but that raises questions about change and becoming. If all moments exist equally, in what sense does time pass? Our experience tells us that time flows, that the present moment is constantly being replaced by a new present moment. But in the Bloch universe, there is no flow. There is only the four-dimensional manifold, static and eternal, and our experience of flow is somehow an artifact of our consciousness moving along our world line. This view is called eternalism, and it contrasts with presentism, the view that only the present moment exists, that the past has ceased to be, and the future is not yet real. Presentism is more aligned with our intuitive experience, but it is difficult to reconcile with relativity, which denies a unique, objective present moment. Growing Bloch universe is an intermediate view, where the past and present exist, but the future does not yet. Time advances, and new moments are continually added to the block. This preserves some sense of temporal flow and aligns better with the intuition that the future is open. But it faces challenges in relativity, where simultaneity is relative, making it unclear which events are being added to the block at any given time. And it is unclear how growing block universe will handle CTCs, where a traveler from the future influences the past, which is supposedly fixed and complete. If time travel is possible, ethics becomes complicated. Do you have a moral obligation to prevent atrocities in the past if you can travel back? Can you be held responsible for actions in the past that were, from your perspective, in your future when you committed them? If your actions in the past are already part of the fixed history, are you truly responsible, or are you merely playing out a predetermined role? These questions blend free will, determinism, and moral philosophy in ways that are difficult to untangle. They suggest that time travel, if it is real, would challenge not just our physics, but our entire conceptual framework for understanding agency and responsibility. Epistemology, the study of knowledge, is also affected. If you can observe the past directly by traveling to it, history becomes an experimental science. You could resolve historical debates by witnessing events firsthand, but you might also introduce observer effects, altering the past by your presence, or you might encounter a problem of infinite regress. If historians routinely travel to the past to check facts, their presence becomes part of the historical record, which future historians must account for, including the presence of even later historians, and so on. The very concept of objective historical truth becomes muddied. In quantum mechanics, the role of the observer is already contentious. Measurement collapses a wave function. But what counts as a measurement? Does it require consciousness? Is collapse a physical process, or merely an update of information? If time travel is possible, these questions become even more acute. If you travel back and observe a quantum event, do you collapse the wave function in the past? Does your observation affect the probabilities of events that have already occurred from the perspective of the non-time traveling reference frame? The many worlds interpretation might offer a way out, where your observation causes a branching, but the past you observe is in a different branch in the past that led to your original timeline. But this multiplies entities, creating a proliferation of branches that may or may not correspond to physical reality. The psychology of time travel is another curiosity. Imagine meeting your past self. You have memories of the encounter from the younger self's perspective, and now you are experiencing it from the older self's perspective. Your knowledge of the encounter is self-referential, a loop with no external input. Where did the information come from? This is the ontological paradox or bootstrap paradox. A classic example is a time traveler who goes back and gives Shakespeare a copy of Shakespeare's plays, which Shakespeare then copies and publishes as his own. Who wrote the plays? The information exists in a closed loop without an originator. This is not necessarily a logical contradiction, but it is strange. Information appears to come from nowhere, violating our intuition that information must have a source. Similarly, you could have objects that loop through time, existing without being created. A watch is given to you by your future self. You keep it for years, then go back in time and give it to your younger self. The watch ages and wears, but it is never manufactured. It exists in a closed causal loop. Where did the watch come from? This is physically bizarre, but not logically impossible if self-consistency is maintained. The watch's entropy might increase each loop, eventually wearing out, which places a limit on the number of loops. But if entropy can be carefully managed, the loop might persist indefinitely. These paradoxes are not arguments that time travel is impossible, but they illustrate that time travel would violate many of our deeply held intuitions about causality, information, and the structure of reality. They suggest that if time travel is possible, the universe is far stranger than we ordinarily suppose. From the standpoint of quantum field theory, time travel introduces problems with the vacuum state. The vacuum in quantum field theory is not empty. It is filled with fluctuations, virtual particles popping in and out of existence, fields oscillating at all frequencies. The vacuum state depends on the space-time geometry. In flat spacetime, there is a preferred vacuum state, the Minkowski vacuum. In curved spacetime, defining the vacuum is more subtle. Different observers might disagree on what counts as a particle. The Unruh effect, for instance, shows that an accelerating observer in Minkowski vacuum detects a thermal bath of particles, a temperature proportional to the acceleration. Similarly, near a black hole horizon, the Hawking radiation represents particles in the vacuum state of distant observers. If space-time contains CTCs, the vacuum state becomes even more ambiguous. Fields propagating around a CTC would have to satisfy boundary conditions that are periodic in time, which constrains allowed modes of the field. The vacuum energy might diverge, or there might be no consistent vacuum state at all. This is part of the reason why quantum effects are expected to destabilize CTCs, the basis of the chronology protection conjecture. The vacuum fluctuations, instead of being small random fluctuations, become coherent and amplified, feeding back on themselves through the CTC, building up to infinite energy density. Calculating this precisely requires knowing how to quantize fields on a space-time with CTCs, a problem that is not fully solved. Different approaches yield different results, and there are ambiguities in how to handle the infinities that arise. Some calculations suggest that the divergence is real and unavoidable, supporting chronology protection. Others suggest that it might be an artifact of the approximation methods used, that a full quantum gravity theory might regulate the infinities and allow stable CTCs. Without a complete theory, we cannot be certain. The relationship between time travel and entropy deserves more attention. The second law of thermodynamics states that entropy increases over time in a closed system. This is a statistical law, arising from the fact that there are vastly more high-entropy states than low-entropy states, and a system evolving randomly is overwhelmingly likely to move toward higher entropy. But the underlying microscopic laws are time-symmetric. So the second law is really a statement about initial conditions. The universe began in a low-entropy state, and entropy has been increasing ever since. If you travel back in time, you move to an earlier cosmological epoch, where the universe as a whole has lower entropy. But you, as a traveler, carry your own entropy with you. You are a localized high-entropy system, a human body, a machine, whatever, embedded in a lower entropy environment. Your presence increases the local entropy of the past. If many time travelers visit the past, they could collectively increase the entropy of the past to the point where the arrow of time is disrupted. But this is unlikely. The entropy of the entire observable universe is dominated by black holes in the cosmic horizon, vastly exceeding the entropy of any plausible number of time travelers. There is also the question of whether time travelers would be able to perform actions in the past that decrease entropy, such as reassembling a broken egg or unmixing a gas. If the past is fixed, if self-consistency holds, then any attempt to decrease entropy would fail. The egg would break again, the gas would remix, something would intervene. This suggests that the second law is enforced not just statistically, but by the consistency requirements of the space-time geometry itself. The universe does not allow you to decrease entropy in the past, because doing so would create an inconsistency. This is speculative, but it hints at a deep connection between thermodynamics, causality, and the structure of space-time. It suggests that the arrow of time, the increase of entropy, is not independent of the causal structure, but is intimately tied to it. Time flows forward because entropy increases, and entropy increases because the universe began in a low-entropy state, and the dynamics are such that high-entropy states are more probable. Time travel, if it is possible, must respect the structure, or else the universe would be riddled with contradictions. Let us consider practical scenarios. Suppose you have a time machine. You set the dial to a date in the past, step inside, and activate the device. What happens? If the time machine uses a wormhole, you enter one mouth and emerge in the other at an earlier time. The journey through the wormhole might be instantaneous from your perspective, or it might take some time, depending on the details of the geometry. If the time machine uses some other mechanism, a Tipler cylinder, a warp drive, a cosmic string, the experience would differ, but the endpoint is the same. You emerge in an earlier coordinate time than you entered. You step out and look around. The world is as it was at that earlier time. People are dressed differently. Technology is older. Historical events that you know have not yet happened. You have knowledge of the future. This gives you enormous power. You could invest in stocks that you know will rise, bet on sporting events, warn people of impending disasters. But every action you take is part of the fixed history. If you warn someone of a disaster, either they do not believe you, or they do but the disaster happens anyway, or the disaster is averted and history records that was averted by a mysterious stranger who disappeared afterward. There are no degrees of freedom. The past is what it is, and your actions are already part of it. This is profoundly claustrophobic. You have the illusion of choice, but every choice is constrained by the requirement that the timeline remains consistent. You cannot do anything that would prevent your own departure, because you did depart, and that is a fixed fact. You are trapped in a predetermined role, acting out a script that is already written. Some philosophers argue that this is no different from determinism in a non-time travel universe, that even without time travel, if the universe is deterministic, your choices are already fixed by the initial conditions and the laws of physics. But time travel makes a determinism more visceral, more immediate. You can see the future consequences of your actions by looking at the present, which is your past. The loop is closed and tangible. Alternatively, in the many worlds interpretation, your arrival in the past causes a branching. The timeline you left is one branch, and the timeline you are now in is another. You can change this past, can kill your grandfather in this branch, because this branch is not the same as the branch you came from. Your grandfather in the original branch lives and has descendants, including you. Your grandfather in this branch dies by your hand, and this branch's version of you is never born. There is no paradox because the two yous are in different branches. But this raises a question. Can you ever return to your original branch? If not, you are stranded in a parallel world, and your time travel is really a form of universe hopping. And if the many worlds interpretation is correct, there are already infinitely many branches, constantly splitting at every quantum event. Adding time travel to the mix increases the branching, but the conceptual framework is already in place. The practical difficulty of navigating branches is immense. If every quantum event causes a split, the number of branches grows exponentially. The branch you arrive in after time traveling might be almost identical to the branch you left, differing only in microscopic quantum details. Or it might be very different if the quantum events that split the branches have macroscopic consequences. Predicting which branch you will land in, or finding a way back to your original branch, seems impossible without a complete understanding of the quantum state of the entire universe, information that is inaccessible even in principle due to the uncertainty principle and the no-cloning theorem. Could time travel be used for computation? Some theoretical studies have explored closed time-like curves as computational resources. A computer with access to CTC could, in principle, solve problems much faster than an ordinary computer, even faster than a quantum computer. The idea is that you send the output of a computation back in time to serve as the input, creating a loop where the computation is self-consistent. The CTC acts as a kind of oracle, providing the answer without the need to perform the full computation. This sounds like magic, but it is a consequence of the self-consistency requirement. The system must settle into a state that is consistent when looped through the CTC, and that state might correspond to solution of a hard computational problem. However, this relies on highly idealized models and assumes that CTCs are stable and controllable, which is far from established. It also raises a question of whether the solution obtained is unique. There might be multiple self-consistent states corresponding to different solutions, or no solution at all. And the physical mechanism by which the system finds a self-consistent state is unclear. It might require an exponentially long settling time, negating the computational advantage. These are active areas of research in quantum information theory and the foundations of quantum mechanics, probing the limits of computation and the nature of physical law. The cultural and narrative fascination with time travel is understandable. Time travel stories allow us to explore counterfactual histories, to imagine how things might have been different, to confront our past mistakes or glimpse our future possibilities. But the time travel of physics, if it is real, is bound by rigorous mathematical constraints and does not offer the freedom that fiction often portrays. You cannot change the past in a way that creates contradictions. You cannot erase your regrets or undo your mistakes unless those very attempts were always part history. The past is not malleable. It is fixed, carved in the space-time manifold, and any time travel merely traces out curves that were already there. This does not mean time travel is impossible, but it means that if it is possible, it is very different from the time travel of popular imagination. It would be a journey through a static four-dimensional structure, following a world line that happens to loop back on itself, experiencing the universe in a non-standard order, but always respecting the overall consistency of the structure. It would be strange, disorienting, and philosophically troubling, but it would not be paradoxical, not in a logical sense, because the universe would simply be what it is, a self-consistent four-dimensional whole. We can also consider time travel in the context of observational cosmology. The observable universe has a finite age, about 13.8 billion years, determined from the expansion rate and the temperature of the cosmic microwave background. Light travel time limits how far we can see. We observe distant galaxies as they were billions of years ago because the light has taken billions of years to reach us. In a sense, looking out into space is looking back in time. The farther we look, the earlier the epoch we observe. We cannot see beyond the surface of last scattering, the moment when the universe became transparent to light, about 380,000 years after Big Bang. Before that, the universe was opaque, a hot plasma of electrons and photons. The cosmic microwave background is the light from that surface, redshifted by the expansion of the universe, arriving now as microwave radiation. Could we use this to observe the past directly, to perform a kind of time travel by observation? In principle, yes. If we could travel faster than light to a distant location, then use a powerful telescope to look back at Earth, we would see Earth's past. The light from Earth's past is propagating outward at the speed of light. If we outrun that light and then look back, we see earlier and earlier events. This is a form of passive time travel, observing without interacting, but it requires faster-than-light travel, which, as discussed, is equivalent to time travel and faces the same difficulties. Without faster-than-light travel, we are limited to observing events at the speed of light, and we cannot observe anything closer than our current light cone allows. Black holes, again, offer a wrinkle. In principle, information that falls into a black hole is not destroyed, according to the resolution of the information paradox, but is encoded in the Hawking radiation emitted over the black hole's lifetime. If you could capture and decode all the Hawking radiation from a black hole, you could reconstruct the information about everything that fell in, effectively time traveling back to observe those past events. This is wildly impractical. The Hawking radiation from stellar mass black holes is incredibly faint, far below the cosmic microwave background, and would take longer than the current age of the universe to evaporate. And decoding the information would require solving an inverse problem of staggering complexity. But in principle, it is a form of time travel by information retrieval. Closed time-like curves could also be used for communication across time. Instead of traveling yourself, you send a message back in time. This is logically equivalent to traveling yourself in terms of causality and paradoxes, but it might be technically easier. A photon requires less energy and engineering than a human. If you can send information backward in time, you can create causal loops of information, ontological paradoxes, self-fulfilling prophecies. You could receive a message from your future self, act on it, and then send the same message back when you reach that future moment. The message exists in a closed loop with no external origin. This is strange, but not necessarily contradictory if the message is self-consistent. Quantum teleportation, a phenomenon in quantum information theory, allows the transfer of quantum states between particles using entanglement and classical communication. But it does not allow faster-than-light communication or signaling, because the classical communication step is limited by the speed of light. Some have speculated that combining quantum teleportation with CTCs might allow faster-than-light or backward-in-time communication. But the details are murky, and it is not clear that this is possible without violating fundamental principles like unitarity or no cloning. The technology for detecting or creating CTCs is far beyond our current capabilities. But there are speculative ideas. One is to look for astrophysical signatures of CTCs, such as unusual gravitational wave signals from colliding black holes or neutron stars, or anomalies in the cosmic microwave background that might indicate topological defects like cosmic strings. Another is to search for evidence of causality violation in particle physics, such as particles that appear to propagate backward in time or violate energy momentum conservation in ways consistent with a closed loop. None of these have been observed, but the search continues. In the realm of tabletop experiments, researchers have studied analog systems that mimic some properties of CTCs. For instance, certain quantum optics setups can simulate the causal structure of a CTC, allowing photons to interact with their past selves in a controlled way. These experiments do not create real CTCs in space-time, but they probe the logical and quantum mechanical consistency of CTC-like causal structures. The results have been intriguing, showing that quantum mechanics can accommodate certain types of closed causal loops without contradiction, lending support to models like Deutsch's, but also revealing complexities and ambiguities that are not yet fully understood. The notion of time itself, at the most fundamental level, might be emergent rather than fundamental. Some approaches to quantum gravity, including loop quantum gravity and certain formulations of string theory, suggest that time is not a basic ingredient of reality, but arises from more fundamental, timeless degrees of freedom. In this view, the universe at the Planck scale is described by a timeless quantum state, and time emerges as a semi-classical approximation, a useful concept for describing the behavior of macroscopic systems, but not a feature of the deepest level of reality. If time is emergent, then time travel might be a question that only makes sense at the emergent level, not at the fundamental level. At the fundamental level, there is no time to travel through, only timeless quantum correlations. This is highly speculative and raises profound conceptual questions. If time is emergent, what does it mean to say that events have a temporal order? How does causality arise from a timeless substrate? These questions are at the frontier of theoretical physics and philosophy of physics, and answers are tentative and contested. But they suggest that our intuitive understanding of time, and by extension time travel, might be radically incomplete, that the true nature of time is something we have not yet grasped. The mathematical structure of space-time in general relativity is a four-dimensional Lorentzian manifold, a smooth space with a metric tensor that has signature negative, positive, 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 or positive, negative, 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 depending on convention. The metric determines distances and intervals, the light cone structure, geodesics, and curvature. The Einstein field equations relate the curvature, encoded in the Einstein tensor, to the stress-energy tensor of matter and fields. Solutions to these equations are space-time geometries, and different solutions describe different universes or different regions of space-time. Some solutions are simple and symmetric: Minkowski space-time, flat and empty; Schwarzschild space-time, a non-rotating black hole; Kerr space-time, a rotating black hole; Friedmann-Lemaitre-Robertson-Walker space-time, describing a homogeneous and isotropic expanding universe. Others are more exotic: Gödel spacetime, rotating and with CTCs; Taube-NUD spacetime, with unusual topology; Alcubierre spacetime with a warp bubble. Each solution is a possible universe, in the sense that it satisfies the equations of general relativity. But not all solutions are physically realized. Some require exotic matter. Some require special initial conditions. Some are unstable or have singularities or other pathologies. The question of which solutions are physically possible, which can arise from realistic matter distributions and plausible initial conditions, is a central question in general relativity and cosmology. It is not fully answered. We know our universe is described, to good approximation, by a FLRW spacetime with small perturbations, evolving according to the equations of cosmology. But the early universe, the interiors of black holes, the endpoints of gravitational collapse, these are regimes where our understanding is incomplete, where quantum gravity is needed, where exotic geometries might be realized. Time travel, as a phenomenon, sits at the intersection of general relativity, quantum mechanics, thermodynamics, and the philosophy of time. It challenges our understanding of causality, information, entropy, and the nature of reality itself. It is a lens through which we can examine the deepest questions in physics. What is time? Is the future open or determined? Is the universe a static four-dimensional block or a dynamically evolving structure? Do the laws of physics permit backward causation? Or is there a principle that forbids it? The answers are not yet known. General relativity allows space-time geometries with CTCs, but it does not require them, and there are reasons to think they might be excluded by quantum effects or other principles. Quantum mechanics might permit CTCs in certain interpretations, but the full story requires a theory of quantum gravity, which we do not yet have. Observations have not revealed any evidence of CTCs, but that does not prove they do not exist, only that they are not common or accessible at scales we can probe. Time travel, if it is possible, would be one of the most profound discoveries in the history of science. It would force a reevaluation of everything we think we know about time, causality, and the structure of the universe. It would open possibilities for exploration, communication, and understanding that are currently confined to the realm of imagination, but would also bring dangers, paradoxes, and ethical dilemmas that are difficult to foresee. Even if time travel is not possible, the study of it is valuable. It pushes the boundaries of our theories, reveals hidden assumptions, and deepens our understanding of the laws of nature. It is a playground for theoretical physicists, a testing ground for ideas about space-time, quantum mechanics, and the interplay between them. And it is a reminder that the universe is far stranger than our everyday experience suggests, that reality at its most fundamental level operates according to principles that are deeply counterintuitive, yet rigorously mathematical and empirically testable. The exploration of time travel is ultimately an exploration of time itself, of the nature of this dimension that seems so different from space, that we experience as flowing, as having a direction, as separating past from future. Physics has shown that time is not what it seems, that it is interwoven with space, that it is relative, that it can slow down or speed up, that it might even loop back on itself. These are not fantasies or metaphors. They are features of the mathematical structure that describes our universe, features confirmed by experiment and observation, features that follow from the same equations that predict the orbits of planets and the bending of light by stars. Whether time travel will ever be realized, whether we will ever build a machine that allows us to journey into the past or leap far into the future, remains to be seen. The engineering challenges are immense, perhaps insurmountable. The theoretical obstacles, the energy conditions, the chronology protection, the quantum instabilities, all conspire against it. But the universe has surprised us before, revealing phenomena that once seemed impossible. Black holes, gravitational waves, the expansion of the universe, quantum entanglement, the Higgs boson. Each discovery has expanded our understanding, has shown that nature is more subtle and more rich than we imagined. Time, the most familiar and yet most mysterious aspect of existence, continues to yield its secrets slowly. We measure it with ever greater precision, probe its behavior in ever more extreme conditions, and refine our theories to account for its subtleties. And as we do, we inch closer to answering the question that has fascinated humanity for as long as we have been able to contemplate the nature of reality. Is it possible to travel through time, not merely forward at the usual rate, but backward to the past or rapidly into the future, exploring the dimension of time as we explore the dimensions of space? The answer, grounded in the physics we know today, is tentative. Time travel to the future is possible and indeed routine, a consequence of relativity. Time travel to the past is permitted by the equations of general relativity in certain exotic spacetimes, but whether those spacetimes can be realized, whether they are stable, whether quantum mechanics forbids them, whether they can be created or accessed, these are open questions. The weight of evidence and theoretical reasoning suggests that backward time travel is at best extraordinarily difficult, requiring conditions and technologies far beyond anything we can achieve, and at worst forbidden by principles we have not yet fully uncovered. But the question is not settled. The universe is vast, ancient, and full of phenomena we have yet to observe. The laws of physics are not yet fully known. Quantum gravity, the unification of forces, the nature of dark matter and dark energy, these are frontiers where surprises await. It is possible that future discoveries will change our understanding, will reveal mechanisms or principles that either enable or definitively prohibit time travel. Until then, the question remains open, a tantalizing possibility at the edge of the known, a challenge to our understanding, a spur to deeper investigation. Time travel, as a concept, forces us to confront the limits of our knowledge and provisional nature of our theories. It reminds us that science is not a collection of immutable truths, but a process of inquiry, of proposing ideas, testing them against observation, refining or discarding them, and moving forward. The study of time travel is part of that process, a journey into the unknown guided by mathematics and experiment, driven by curiosity and the desire to understand. The universe, in its four-dimensional space-time structure, is a vast and intricate tapestry, woven from the threads of events, world lines, and causal connections. Every moment is a point in this tapestry, connected to every other by the geometry of space-time, by the curvature induced by matter and energy, by the quantum fluctuations that fill the vacuum. We are embedded in this tapestry, our world lines threading through it, our experiences a sequence of three-dimensional slices through the four-dimensional whole. Whether those world lines can loop back, whether we can trace a path that returns to an earlier point, whether the tapestry permits such loops or forbids them, these are questions that touch the very fabric of reality. And so the inquiry continues, physicists calculating, experimenting, theorizing, searching for answers in the mathematics of curved space-time, the probabilities of quantum mechanics, the patterns of astronomical observations. The question of time travel is not merely academic. It is a question about the nature of time, the structure of the universe, the possibilities inherent in the laws of physics. It is a question that challenges us to think deeply, to set aside intuition, and follow the logic and mathematics wherever they lead, even if they lead to conclusions that seem strange or paradoxical. In the end, time travel may remain forever beyond our reach, a feature of exotic space-times that do not exist in our universe, or a possibility excluded by chronology protection or quantum consistency. Or it may one day become reality, a technology of an advanced civilization, a doorway through the centuries, a means to explore not just space but the dimension of time itself. We do not yet know, but the pursuit of the answer, the exploration of the question, the rigorous application of physical law to the possibility of time travel, this is a journey worth taking, a journey that deepens our understanding and brings us closer to the ultimate goal of physics, to comprehend the nature of reality in all its depth, beauty, and strangeness. The traveler who might one day step through a wormhole, who might loop around a cosmic string, who might navigate the warped space-time near a rotating black hole, would be venturing into a realm where past and future lose their ordinary meaning, where causality forms closed loops, where the universe reveals a structure that defies intuition, yet obeys the stern and elegant laws encoded in the equations of relativity and quantum mechanics. That travel would not be violating the laws of nature, but exploring a consequence of those laws, a consequence that is strange and subtle, and perhaps, in the end, as deeply woven into the fabric of space-time as the speed of light, as the curvature around a star, as the expansion of the universe itself.